I'm going to speed through the operation of the transistor as a switch. The transistor comes in many different forms, but we're particularly looking at the bipolar junction transistor, which is the first transistor that was made. It's the common or garden transistor. Let's try and put a bit of flesh on the bones. If we go back to the work we did on a diode is constructed of P and N type material. So a diode looks like this. And just a quick reminder, to turn a diode on, we need at least 0.6 volts across the PN junction to make it conduct. So a transistor is a sandwich of particular materials. So we've got N, P, N. We could have PNP, talk about that in a second. So we have a sandwich of N and P type materials, and the terminals are called the collector, the base, which is the middle one, and the bottom one is the emitter. So collector, base and emitter, and as a symbol that now looks like this. So that's the basic symbol: base, collector and emitter. So here we required 0.6 of a volt to make a PN junction conduct, just for a diode. And as we progress through the next couple of pages, from the base to the emitter, we have the same condition. We need 0.6 to 0.7 of a volt across that PN junction on the base and emitter. So that's a very brief introduction. Let's look at the two different types of transistor. So we've touched on one here, NPN, NPN. So that looks like this. So the three terminals again: base, collector and emitter. The emitter always has the arrowhead on it, and the arrowhead indicates the direction of flow of current through the transistor. In short, we will put a tiny amount of current in the base to turn it on. We'll talk about that again shortly, but the main current flows in the collector and it flows through the emitter and out down there. So this is how we get it to work. We put a small current into the base and the main current flows in the collector and out of the emitter. So this is the main current flow direction on the emitter terminal. So that is NPN. A quick memory aid at this point is not pointing in. The arrow is pointing out. So the arrow points away from the transistor, not pointing in. It has a complementary transistor, which is just the opposite, PNP. So very quick sketch. Arrowhead, always the emitter, the collector, and the one going into the flat side is the base. So I tend to draw my transistors just like this, and like I started over there a moment ago, but often they are drawn with a circle around them. Personal preference, I don't like the circle because it just causes a little bit more clutter on the diagram, making it sometimes a little bit more confusing for you to see what's going on. Okay, so let's just look a little bit more about how we turn this transistor on. And I'm going to concentrate just on NPN from now on. NPN transistors are many times more popular than PNP. They're easier to make, and it just happens that with the way that most of our supplies work, it makes them easier to use and operate. So how do we turn this on? You need a power supply. So let me say, to start with, we've got a simple battery, and it doesn't matter what the voltage is. So this could be anything. Let's say 12 volts. Oops, 12 volts. So there is our power supply, and we're going to want to turn a transistor on. Let's make the load quite simply a lamp. So this circuit is quite pointless. I'm just trying to show how we get this lamp to light. That's all this is about. So what we need to do, is we find a way of passing a small current into the base. For this to flow, we will have 0.6 volts there. This is a PN junction going from the base to the emitter. If we don't have 0.6 of a volt, we won't allow this current to go in, and the transistor will not turn on. But if this condition is met, we've got 0.6 of a volt from the base to the emitter. We can pass a tiny current into the base, and let's say, for the sake of argument, it's 1 milliamp, so it doesn't have to be big. And once we've got that current flowing down there, it causes a huge flow of current, and the current will flow from this end of the supply, the positive of the supply, through the lamp, through the transistor, and out through the emitter. And this current, let me just put a simple number on it, is 500 milliamps. It depends on what the resistance is of the lamp, obviously. But my point here is a tiny current in the base, a milliamp, produces a huge flow of current from this end of the supply to this end of the supply that goes through the transistor. In this case, it's 500 times more. That's not uncommon. Typically, turning a transistor on will produce a current in the collector, so it's coming down through the collector, hundreds of times bigger than the current that we put into the base to make it turn on. Okay, so that's just an intro to it. One little thing. When we use electronics, they tend not to draw this onto the circuit. They tend to just write across the top. This is plus 12 volts, and the bottom end will be 0 volts. So we know there's a supply, in this case a battery. We know it's there somewhere, but they don't bother drawing it. And this may have a name, plus VCC or something like that, but label it at the top and the bottom, and that's all we tend to do. So let's move on and look at a simple circuit which you may encounter. So this circuit is a dusk till dawn light. So this is the sort of thing you may see outside people's front doors, over a porch, and as it becomes dark we turn on a light, and the lamp that goes with that is usually mains rated, so a 230, 240 volt lamp, and we need a means of turning it on, and it's the electronics that turn on that lamp. This circuit is one way of achieving that very objective. So let's have a look at what's going to go on just here. The aim is to get 0.6 volts across the base and emitter and pass a tiny current into the base. If we do that, a current flows from the top of the supply to the 0 volt, so from positive to negative, it flows through the relay coil down to there. The relay will energize, these contacts will close, and we put main supply onto this lamp, so the lamp will light. Just building it up one step at a time. At this moment in time, these are the components we're using. A relay, which I've selected 10 volts, which is an unusual supply voltage, but it's just a convenient number. So we'll have a 10 volt relay. This is an LDR, light dependent resistor. A quick word about an LDR. Its resistance changes with light. So in total daylight, in bright sunshine, for example, it may have a resistance of 1 kilo ohm, 1000 ohms. As we reduce the amount of light that falls on it, for example, the day begins to reach dusk and then go to darkness, the resistance of this increases. And in total darkness, it may have a resistance of 1 megohm. So the difference from daylight to night is very different. So what we're trying to achieve here is to produce a voltage here that reaches 0.6 volts, and that will forward bias the base and emitter and allow this to turn on. So this is just a fixed resistor, and this is a variable resistor which is dependent on the amount of light falling on it. Once we get the key voltage here, this turns on, the relay engages, the contacts close, and the lamp illuminates. So that's the aim that we're trying to achieve. Let's take that one step further. Right, so during the daytime, I've put a 100 kilo ohm resistor here, and if you think about what I'd said previously, we're probably going to have 1 kilo ohm here in bright light. So using some simple figures, and this is just why I chose the 10 volts, very, very roughly, we're going to have 1/100th of the supply voltage across here. It's not strictly 100th. I would have had to make this 99 and this 1K to make that 100th, but that doesn't matter. The numbers are so big, 100,000 and 1,000, 100K, 1K. This is going to give us here a very small voltage. So 0.1 volts. With 0.1 volts here, this transistor is off. So that is approximately equal to 0.1 volts across there. Incidentally, I'm drawing my arrows from here on the base to here on the emitter. I could draw it just there, from there to there. This connection is exactly the same point in the circuit. So whether I draw it round there or there makes no difference. So during the day, this resistance is low, the voltage here is low, the transistor is off, the relay won't engage, and the lamp will be off. So as we move to night time, the voltage across here is going to rise, just because this is a series resistor circuit. The voltage across here may at the moment be 0.1. If this goes up to 2K, this will be around about 0.2. As this rises 5 kilo ohms approximately as it gets darker, this will reach around about 0.5, and we're very close to turning the transistor on. So then we get to the magic point where there is sufficient darkness to raise the resistance of this, and we will get 0.6 volts across there. In getting 0.6 volts here, we pass a current down there. That brings the main current through here. The relay engages, the contacts close, and the lamp will illuminate. So that is a dusk till dawn light. What I suggest you do now is go back to the start, stop and start, pause and play, look at the steps of the video again and again until everything makes sense to you. You're only looking at how to turn a transistor on and the different types of transistor, NPN, PNP.